Hello, this is the content lecture for Environmental Science and Biology 1.2. Again, both of my classes have very similar content right now, so their content lectures are going to be identical. That will change at the end of this unit. You guys will also be doing a few different exercises, so you'll be seeing different things on the LMS. Remember, if there's anything in this lecture that you have questions about, feel free to send me an email or contact me as soon as you have those questions. I also encourage you to reach out to each other, ask each other questions, build those relationships, and see who you can lean on for their understanding. I don't know everybody right now. I'm still working on that. As I get better about that, I might even be able to point you guys in the right direction to help each other. This is also the last video I will be recording before class actually starts. So any feedback that you have given me, I haven't been able to implement yet. From my end, it looks like these are loud enough and clear enough, but either of those are not true. You need to let me know as soon as possible. All right, for 1.2, we're going to be talking about how do scientists represent their findings. All right, the main way that scientists do that are by using statistics and with modeling. Before we talk about, though, I want to go over the difference between qualitative data and quantitative data. So quantitative data is numbers, anything that you're measuring, anything that you can describe with hard facts that are objectively true. All right, so anything that we measure with a ruler or a graduated cylinder or a scale, anything that you can measure is going to count on here. There are some things that are qualitative that we can measure and turn into quantitative data, and I'll get to that when I talk about qualitative data. So the examples here on the left side of your screen are going to be our go-to here, right? So anything with number I already mentioned. So temperature, volume, height, width, depth, concentration, so how concentrated something is, shape, if it is cubic, if it is hexagonal, any of those words we learn in geometry, those count. Texture can be quantitative if we know the grit. So if you've ever looked at sandpaper or shopped at Lowe's or Home Depot with your parents, you might see those in 120, 200 grit, up to 1,000, 1,200 grit for almost a polishing instead of a sanding or removing of material. Qualitative data, on the other hand, is going to be something that's more of an opinion or relative. So color looks the same, a little bit different to everybody. So your blue may not exactly look the same as something that I call blue. But if we measure the color with, say, a hexadecimal number or a hex value, or if we look at the frequency of light that color is, like, say, 550 nanometers for red light, whereas the blue light on my mouse is going to be closer to 1200 nanometers. We can also describe things. If it's big or small, loud, quiet, rough, smooth, these are relative. So they're comparing it to something else. You could also have opinions in qualitative data. If you say something looks gross or smells pleasant, that counts as qualitative data. If it smells good. But if you say it smells like vanilla or banana, those are going to be quantitative data because we know what those things smell like. All right, I'm going to get my head out of the way. All right, so this is just a review slide to give you more information about quantitative versus qualitative. Quantitative, if you think about it as answering the what, where, how, when, and who questions, you're usually on the right track. If you're doing qualitative data and it answers the how, that's also a good way to remember it. I generally do measurements versus opinions or hard fact versus relative as the way that I remember it for science. Right. Quantitative data can be analyzed with statistics. We aren't going to do a whole lot of statistics in these classes, but we are going to do means and we are going to look at distributions. So I want to talk about those. The mean is just the average. If you guys have done arithmetic averages in your math classes, that's really easy. It's where you add up all the different values and then you divide by the number of values there are. We'll have some examples of that in the classroom exercises that you guys will be doing. So if you don't quite remember what that is, that's okay. We'll get to it. Distribution, as you can see in this graph on the right side of your screen, is how those actual data are arranged. So these are densities of different things being measured. This graph doesn't tell us the x scale, the x-axis, what that is being measured for, but it doesn't matter for what I want to talk about. So you can see that most of the densities are around here, right? From something like 0.75 to 1.75. And there's not a lot way up here at the very dense 2.25 to 3.0. All right? So it's distributed to the left here. You might have heard of something called a bell curve. Bell curves talk about distribution as well. Each of these columns in this graph would be a sample. And you can think of a sample as a group of individuals or events that are occurring. It's any data that you're collecting, you could generally call a sample. These are also vocab words, so Quizlet's going to be a great resource for memorizing those, and I've got some more info over there. We can also look at probability and risk when we're talking about quantitative analysis. So probability is just how likely an event is to happen. So on these six-sided dice, right, if I were to roll a single die, that's one of these, I would have a 1 in 6 chance that any of those numbers are going to pop up. If I want to, say, get a 4 or a 1, I would have a 2 in 6 chance because each of them are 1/6. Now, if I'm taking 2 die, right, 2 six-sided die, and I want to come up with the number 5, there are more ways to get that than just rolling a single 5, right? I could roll a 1 and a 4. I could roll a 2 and a 3. Or those numbers could be switched on the die, right? Die A could get a 2 and die B could get a 3. Or die A could get a 3 and die B could get a 2. So there's much more ways for that to happen. So probability is just looking at how likely it is to happen. We're going to have a discussion about that and a short video for you guys to watch next week. Risk is just looking at the probability of something that you don't want to happen, something bad to happen. So if when you're rolling one of these six-sided die and you do not want a 1, your risk of getting a 1 on a single die is 1/6 of the time. And if you need to give that in a decimal form instead of a fraction form, you just take 1 and divide it by 6 on your calculator, right? Easy. The other way that scientists show their information is through models, because it's sometimes a lot easier to look at a picture or a 3D example than it is to just use words or to just use numbers, right? This thing over here that looks super complicated is a model of deoxyribonucleic acid, DNA. It is double helixed, and this allows you to see all the different parts of it without me having to give a 5-minute lecture on it. Biology class, you're going to get some more information on this. Environmental science, you've already got DNA covered, so we're not going to do that. We're going to look at other stuff. It's just an example. So these are the main ways that I want you to know about physical models being used. Physical models, like this actual sculpture, this is a thing you can buy and play with. You can use your hands to manipulate it. Graphical models like maps or 3D renderings of things, simulations are ways to do that. If you have watched the weather on the news, you've seen radar forecasts, forgot the word forecasts, of what will happen. Those are graphical models. Conceptual models, on the other hand, focus on relationships. These are usually done with diagrams or drawings, sometimes even just through verbal descriptions. Flowcharts and concept maps are all conceptual models. You might have seen a few of these in textbooks, and you'll be seeing a few examples of these in the coming months. Mathematical models are what we do if we take some information and try to fit a equation to it. So if we go back and look at this, you can see this blue line here, this dark blue line, that could be modeled with a algebraic expression, right? This is just a curve that flattens eventually. We can write that as a mathematical expression. You guys may not have the math skills to do that. Mine are a bit rusty on it. I don't blame you. I just want you to know that that's something that could happen. All right. So how do scientists represent their findings? We use physical models, graphical models, conceptual models, and mathematical models to represent findings. But we need to remember that there are some steps to get those, right? We already talked about the scientific method. We've talked about some different types of data now. You guys are going to do some exercises, and you're going to work through even a couple reading graph exercises that I want to get you guys through so I know what you guys are familiar with versus not familiar with. As always, if you have questions, I want you to send me an email. Get in contact with me. I do not have any other way to help you if you don't let me know you're struggling. Otherwise, I'm going to see grades and I can only react to those grades, right? But then you've been graded on it. I want you to get help before you earn those points if you need it, all right? Use my free time at the end of the day, right? 2 to 3 every day. On Fridays, it's longer because I've got some more free time on Fridays that I've built in so I can help you. So go to that calendar on the class page and use my appointment slots to get some office hours helps, all right? If you're not available during those times, send me an email. We might be able to work something out.